Okay, in this video we're going to check how one can the equivalence of Newton's second law and Lagrangian mechanics, the Euler-Lagrange equations. So let us recap Newton's second law. Newton's second law says that the net force acting on an object is equal to the rate of change of its linear momentum. So this can be expressed as F, which is equal to the force, and this is m times acceleration, and the acceleration is just x double dot. So this is m times x double dot. Now typically the force can be written as the gradient of a potential, dv by dx. So for example, if you have a body which is close to the earth, then the potential is m times g times h, right? So dv or m times g times x. So dv by dx is then minus dv by dx is minus m times g. So for a body in a gravitational potential close to the earth, we have that m times x double dot is m times g. So that's just a small example to show, minus mg. So that's just an example to show how the potential, an example for a potential. So now what we want to do is we want to show how Lagrangian mechanics is equivalent to this equation over here. So one thing you have to remind in Lagrangian mechanics is the quantity called the Lagrangian. So the Lagrangian is equals to the kinetic energy minus the potential energy. Now this minus is somewhat mysterious, but it actually works out perfectly well. So, and usually the Lagrangian is going to be a function of x dot and t. We will ignore time dependence for now, explicit time dependence for now, and just consider a Lagrangian which depends upon x and x dot. So we're going to scratch that, x and x dot. So now the principle of least action basically says that the action, which is denoted by s, is the integral over dtl, right? Now the principle of least action says that trajectories of Hamiltonian systems follow basically the path of least action. So in order to calculate the least action, we take the variation of it. So we have delta s is equals to delta of the integral over dtl. Now if we take the variation, we get this is the integral dt delta l. And now since L is a function of the position and the velocity, we have dt, and let's write delta L of x and x dot. Now to calculate delta L, we just take the derivatives, right? So we take partial L by partial x dx plus partial L by partial x dot delta x dot. That is the change of the Lagrangian. So we get that this guy is just equals to the integral dt partial L by partial x delta x plus partial L by partial x dot delta x dot. Now what we can do is we can write this on a bit nicer. So we have dt partial L delta x plus partial L by partial x dot, and now we have x dot. We write x dot is dx by dt. So we have delta dx by dt. And now we're going to do a small trick. We're going to say that we can exchange the operation of taking the variation of delta and d by dxt. So this is just dt partial L by partial L delta x plus, and now I'm going to swap the order of the variation. So this is d by dt partial x, d by dt delta x. And now I'm going to do another trick. I'm going to say that d by dt partial by partial x dot delta x. I'm going to apply the product rule here, and I'm going to say that this is equals to d by dt partial L by partial x dot delta x plus dl by dx dot d by dt delta x. And what we do is just we rearrange this a little bit. So we take this is the expression we have over here. So we're just going to take this term to the left side, and then we have d by dt partial L by partial x dot delta x minus d by dt partial x dot delta x. Delta x is partial L by partial x dot d by dt variation of x partial x dot d by dt. Okay, so now we can substitute for this one in here just this stuff. So then what we get is, remember we have the action delta s is integral dt. We have this term over here, which is dt partial x delta x, and then we have plus d by dt partial L partial x dot delta x minus d by dt partial x dot delta x. Okay, so now we have to remember the following. When we take the variation of the action, what we actually have is the following. We have our trajectory of our particle, we have our time, for example here, and x here, and then we have 2 points, the initial point and the final point, and then we have a certain trajectory where the particle moves along. Now this point and this point are fixed, so when we take the variation, we actually look for different variations of the path. So we have here delta x. So why this is important is for the following reason. When we take the integral of this term here, this is a total derivative with respect to time over here, this t here, right? We're integrating this over time, so this is just going to give a point. This is just going to give, this is from the time ti to time tf. So delta s is the integral d time partial L by partial L delta x minus d by dt partial L by partial x dot delta x. And now if we integrate this term over here, we have the integral, and we have partial L by partial x dot delta x, and this is between xi and x. Well, actually it's between ti and tf. Now don't forget that this delta x is actually a function of t, right? Because we have different trajectories, and at each time point we perturb the the actual trajectory by amount delta x. So this is basically integral dt partial L by partial x minus d by dt partial L by partial x dot times delta x. So I've taken out the common factors delta L, delta x, and then this is plus delta L, delta x dot, delta x of tf, delta x of tf minus partial, this is also minus delta L by delta x dot, delta x of ti. And now these terms over here are just equals to 0, so they vanish. So because in this we said that when we perturb the path, we start with fixed initial condition and fixed final condition. So these two are equals to 0. So this is equals to 0 and this is equals to 0. So what we end up with is the integral over dt partial L by partial x minus d by dt partial L partial x dot delta x. And now this delta x is arbitrary, and if this is, we said we want to extremize the action. So if we go back up here, this should be equals to 0, because we want a maximum or a minimum of the action. So if this is to be 0, then this must be equals to 0, because delta x is arbitrary. So we end up with what is called the Euler-Lagrange equations, which is d by dx minus d by dt partial L by partial x dot is equals to 0. Or we can equivalently write partial L by partial x is d by dt partial L by partial x dot, and this is known as the Euler-Lagrange equation, right? And now what happens if now we want to explain Newton's second law, remember? So we say that the Lagrangian is the kinetic energy minus the potential energy. The kinetic energy is usually 1/2 mx dot squared minus, and the potential is a function of x usually. So we can calculate now partial L by partial x dot, which is just, since this term is independent of x dot, we just get the square down here. So this is m times x dot, and partial L by partial x is just minus dv by dx. And if we look at the Euler-Lagrange equation, we have this term which is over here and this term which is over here. So if we plug in, we get minus dv by dx is equals to d by dt mx dot, and the right hand side is just m times x double dot. And remember, we said that the force is equals to minus dv by dx, so we get that the force is equals to m times x double dot. So as we showed, basically that the Euler-Lagrange equation reduced to the Newton's second law reduced to the Newton's second law. So that's it.